Hi folks, so I'm making this video here to help you with these problems about applying Newton's second law in radial coordinates here. So in this example, imagine this particle right here moving along this path where, presumably this path is described where we have some sort of r against theta. And at the instant shown, the velocity vector, if I were to draw it, might look something like this. And it's important to note that the velocity vector is always tangent to the curve. The normal force, if I were to draw this normal in, might point something like this. And you'll notice that there is an angle between the normal and the radial direction here. So I'm going to call that angle alpha. And you need to be able to find the angle between the normal forces and the radial direction in order to write the Newton's second law equations. So now, notice if I put an r hat and a theta hat here, right? So the r hat direction is this way, outward. Then the theta hat direction would be this way. And notice now that there's an angle between the velocity vector and the theta hat direction. And that's the same as this angle right here. So I'm going to go now work through the steps involved in how would you go about finding this angle. So imagine this particle now. I'm going to draw a picture of it. Here it is at a point in space. And imagine it moves over a distance. Let me call that distance ds here. So this ds, this is a small displacement vector. And there's different ways we can write that ds. We could write it in terms of Cartesian coordinates, in which case we could call it like a dx and a dy. Might look something like this. Dx, dy. Or we can also write that ds vector in terms of cylindrical coordinates. If we do now, instead of imagining a small change in s, imagine a small change in theta. Now when theta changes, what we're going to get is a small displacement vector that looks like this. Right? And this thing's magnitude is going to equal r times d theta. Then imagine a small change in r. Right? So that's going to be a dr. So in this picture over here, imagine this object. It moves from here to here, a small displacement. What we're doing is we're writing this displacement in terms of vectors that are linked to changes in our coordinates. So imagine theta changing by an amount d theta. So that displacement vector would be this way. And its magnitude is r d theta from definition of a radian. Then imagine r changing an amount dr. Right? So that's what this triangle, r d theta times dr, is equal vectorially to ds. In this picture it would look like this. This angle alpha would be this guy here, that interior angle. It's not the best triangle I've ever drawn, but the tangent of the angle alpha would equal dr over r d theta. So that would equal 1 over r dr d theta. So in this example, presumably I know r as a function of theta. 1 over r dr d theta would allow me to find alpha and then move on with the free bodies and writing of the Newton's second law equations. So I'll try to work out some examples here that illustrate this, and hope you folks have a good night.